Welcome to section 5.1. In this section, we're introduced to the idea of what they call a probability distribution. And there's a definition that they use which is really good. A probability distribution is a graph. Actually, let me put another word in there first. Is a table, graph, or formula that assigns every outcome I'll put an associated probability. And so this definition transcends both chapters 5 and 6. And so as we're in chapter 5, they might ask again about the two definitions and being able to tell whether something's discrete or continuous. So if something is discrete and continuous, I told you in the very beginning that I wouldn't have you learn a definition that wouldn't be used later on. And so if you remember, something that's discrete is countable, right? There's just a certain number of ways that could happen, not an infinite number of ways. So the number of girls in a family, definitely discrete. There's nothing between having 2 girls and 3 girls in a family. Temperature outside, definitely continuous. Between 41 degrees and 42 degrees are theoretically an infinite number of degrees, and therefore it is continuous. And so as we go to handle these things, the reason why they care about those definitions is if something is discrete, then we're going to handle that very easily in a table. But if something is continuous, a table won't work because I can't include all the values. So we're going to have to do a graph or a formula. For our class, because we don't know Calc 2, we're going to be using a graph, not a formula. The formula is going to be used if you take the next level stats, which typically has a Calculus 2 prerequisite to it because of the formulas that you have to deal with. And not just because of the way they look, but because of the calculus that you have to do to unlock the same answers that you and I are going to get from a graph or a table of values. Right? So just to keep that in mind, they may ask for discrete and continuous. Again, it's just the same thing as it ever was in chapter 1 and 2. So I'm going to get rid of some of these things. In 5, we're going to focus on discrete probability distributions. And so we're going to be able to represent those in a table format. So one of the examples that I always share is something that I believe that everybody can understand. For the most part in this section, you're not coming up with the probability distribution. In fact, I think that's going to be all the case. They're going to give you one, and then they're going to ask you to find its mean and standard deviation. Now, that could trigger you a little bit when you think of the work from chapter 3 that the mean and standard deviation has. It's way less work for this. Because you're dealing with probabilities, some of that work is pre-done for you, and so it goes really quickly. So let's talk for just a minute. Let's suppose we have a single 6-sided die. And we're going to roll that die. Now, we want to find the probability distribution. Of this event. Easily done if we know the definition. Right? So this is one that you and I could come up with. So let's go do it. X is always going to represent a specific outcome. And what we need to do is for every outcome, right next to it, its associated probability. So think about rolling the die. What are the outcomes that are present, or that could happen? A 1 could come up, a 2 could come up, a 3 could come up, a 4 could come up, a 5 could come up, and a 6 could come up. And the probability that a 1 comes up is really nice. It's just one option out of 6. Same with the 2, same with the 3, the 4, said 4 and was writing at the same time. They're all 1/6. They call this a uniform probability distribution because all the probabilities are the same. That's it. Let's make some observations off of this one. The first thing I want you to observe is look at what the sum of the probabilities is. What is 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6? Add it up and you're going to get 6/6 or 1. That's how you know whether you have a probability distribution. In a probability distribution, the sum of the probabilities is 1 always. So they may have a question in there. If you look through the book's written homework, they definitely have it in there where they say, is this a probability distribution? You're literally checking to make sure the probabilities add up to be 1. They also stress that they are probabilities and will list this property as well, that all the probabilities are between 0 and 1, but that's just a natural occurrence of that. I don't want you to think that these probabilities are always the same. So it just happened to be the same because the probability of getting 1, 2, 3, 4, 5, or 6 on a single row of a die is the same. What if I did something like the number of girls? When a couple has. And then I'm going to take something that I know you did in the homework, 4 children. So we're back to 4.1 in terms of that setup. And we're going to have to remind ourselves about something. Okay, if they had us come up with this, we would have to think about, well, what are the outcomes? We could have absolutely no girls in the births. We could have 1 girl and the other 3 are boys. We could have 2 girls and the other 2 are boys. We could have 3 girls and then the other child is a boy, or all 4 could be girls. And each one of those has a probability. So what I've done every time is listed out every single outcome individually. And now we're going to be able to figure out its associated probability. Again, these charts are typically given to you and you're asked to do something with it. If we're going to be able to answer this, we either have to remember or recreate what we did back in chapter 4. And that is that we said, oh, one of the options, let's have a boy be born first, is boy, 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 boy. We could have 1 girl with a boy being born first, and that girl could be in the 2nd baby. The girl could have been the 3rd baby, or the girl could have been the 4th baby. Well, still with the boy being born first, we could have had 2 girls, and it could have looked like that, or it could have been boy, boy, girl, girl, or it could have been boy, girl, boy, girl. And we could also have a boy and 3 girls. That exhausts everything with the boy being born first. Now let's let a girl be born first. We could have all girls. We could have a single boy. Single boy. I forgot what I was doing. And we're very methodical about this. So hopefully this example made sense to you when you did it back in 4.1. We could have had a couple of boys and they could both be in the middle. We could have a boy, boy, girl, girl, boy situation. We could have the boys being born together at the end, or we could have had 3 boys. So this is what you would have listed out. The book shows you with 3 children. You were asked to do it for 4, I think, in the homework. You have 16 options. How many of them have no girls? Let's go figure out how many have no girls. This one right here, whoops. Actually, I'll do that. I'll highlight it in yellow. Only 1 out of 16 had no girls. Let's go to a different color, blue. 1 girl. Here's 1 girl. Here's a second 1 girl. Third 1 girl. Let's go over here. 4th 1 girl. And so it looks like there's 4 out of 16, or 1/4. Okay, so 4 out of 16, 1/4 with those blue crossouts. 2 girls. We'll cross those out in red. Here's 2 girls. Here's 2 girls. Here's 2 girls. That's 3. Here's 2 girls. Here's 2 girls. Here's 2 girls. 1, 2, 3, 4, 5, 6. That's 6 out of 16, or 3/8. Let's go get 3 girls. What color can I use now? I haven't done green yet. I don't know if that will show it very well. But 3 girls. Here's 3 girls. And here's 3 girls. Here's 3 girls. Here's 3 girls. So that's 4 out of 16 again. For 1/4 again, notice that they're coming right back down. And then what's the only thing we haven't crossed out? I'll do that one in black. This guy right here, where all 4 are girls. That's 1/16. So you could have the probabilities like that. My point is, in doing this with you, is to just stress what a probability distribution does. It puts the outcome with the probability of it happening. Take a look at what this is. What's 1/16 plus 1/4 plus 3/8 plus 1/4 plus 1/16? Now you can quickly say, well, it's 1 because you did it, but let's make sure we did it right. 1/16 plus 4/16 plus 6/16 plus another 4/16 plus 1/16. And we have 5, 11, 15, or 16/16. We're not shocked that that equals 1. So whenever you add up the probabilities, you should always get 1 when you're given a probability distribution. Because this is a video, I'm going to erase this work here, knowing that you could back it up and pause it if you wanted to see it again. But we're going to use both of these examples in order to do the lion's share of what's been asked for you in this section. So in this section, they're going to say, hey, is this a probability distribution? Or it will already be. If it's not a probability distribution, you'll note that it doesn't add up to 1. Or if it does add up to 1, but one of them happens to be negative or over 1, then you can state that as well. So you'd be looking to establish whether it's a probability distribution just by seeing if the probabilities add up to be 1. When it is, they typically ask you to find the mean and the standard deviation. So coming right back up here, I'm going to talk to you about what the mean is. The mean for a probability distribution is going to have a unique symbol. Okay, it's not going to be x bar. X bar is the sample mean. So x bar is the sample mean. When we do the mean of a frequency table, they're going to use mu. Now the reason why they do that is the probability distribution talks about what theoretically happens for the entire population. And so they're going to use the Greek letter mu. That's my best attempt at it. It looks like a very deep U. You can see that it looks like an M. It's pronounced mu in there. It has an M sound in it. And here's all you have to do in order to find the mean. Take the sum of each outcome times its associated probability. And you're finished. So if we go to find the mean of this one right here, we are going to have to tack on another column. And maybe, let me get rid of those lines for just a minute. Let me do them in a different color. Let me do them in blue. So you're going to be given a probability distribution which is represented in black. And then they're going to ask you to find the mean of the probability distribution. Well, you're going to go look for the formula. Oh, there's the formula. What's it say to do? Add up the x's times their p of x's. Well, I got to find out what those are. Now, I'm going to do this without reducing the fraction so everybody is staying together. 1 times 1/6, 1/6. 2 times 1/6, 2/6. 3 times 1/6, 3/6. 4 times 1/6, 4/6. 5 times 1/6, 5/6. 6 times 1/6, 6/6. And what am I supposed to do with that? That's not my mean. All I'm supposed to do, and take a look at this formula, only do what the formula says. Add them up and be done. When you take the time to add them up, you are finished. You can think, well, I know that I learned that you're supposed to add up all the data and divide by the number of data points. So I should add these up and divide them by 6. Well, no, that's not the formula. These aren't data points. These are outcomes with their associated probabilities. You are done by just doing the product and adding them up. So the mean is simply the 1 6 plus the 2 6 plus the 3 6 plus the 4 6 plus the 5 6 plus the 6 6. So what is that? 3, 6, 10, 15. That's 21 6. What's 21 divided by 6 as a decimal? 3.5. Of course it's 3.5. These things are equally balanced. It's smack right dab in the middle. 3.5. That's exactly where we would have expected to find the mean. So there we go. That's how you find the mean of this guy. So the mean is simply the addition of this blue column at 3.5. So the mean is 3.5. The mean of this situation, easily found, right? What do we have to tack on? An extra column. What's that column? According to the formula, it's x times p of x. And just let the formula be your guide. 0 times 1/16, 0. 1 times 1/4, 1/4. 2 times 3/8, 3/4. You okay with that in doing that? 2 times 3 over 8, 3/4. 3 times 1/4, 3/4. 4 times 1/16, 4 over 16, or 1/4. And if I add them all up, I get 1/4, 4/4, 7/4, 8/4. I get the number 2. The mean is 2. You don't have to do any division or anything. Follow the formula. Write it down and follow it. The mean is just flat out 2. Now, does 2 make sense? Let me circle 2. 2's right in the middle. And take a look, there's balance on both sides. Sometimes it won't be right in the middle. It's going to be where the heavier part of the data is, and we can look at an example of that. But this is what you're doing throughout the 5.1 section, is you're determining what the mean and the standard deviation are using these formulas. Okay. And this is all in the 5.1. Now, they may have some questions where you're interpreting the information that's being presented to you. We could look at those as well. Now, I did mention that we are going to ask us to do the standard deviation. So I'm going to box this in blue, since the work that I did was in blue for the mean. And then when I go to write the standard deviation formula, I'll put it in red. It looks like this: the sum of the x squareds times p of x's minus the mean squared and the whole thing square rooted. The key, though, is if we ever had to round a mean, this needs to be the unrounded mean being put in here. Okay, that'll make more sense when you're in the problems. If you ever had a mean that went on for that you rounded off, you need to use the full expansion of that mean there. It makes a difference, especially if the standard deviation is low. Okay, so what is this saying to do? Well, it's saying to take some numbers and add them up. What are those numbers? Those numbers are x squared times p of x. So x squared, 1. 1 squared times 1/6, 1/6. 2 squared, 4 times 1/6, 4/6. 3 squared, 9 times 1/6, 9/6. 4 squared, 16 times 1/6, 16/6. 5 squared, 25 times 1/16. 1/6, sorry. 5 squared, 25 times 1/16, 25/6. Sorry, times 1/6. I apologize for saying 16th. 6 squared, 36 times 1/6, 36 over 6. Now let's add them up. 4, 5, 14, 20, 30, 55, 61, 91 over 6. I think I did that right. Let me go in with the calculator. I just wanted it so you didn't have to look down at a calculator. You could just, 91/6. So what's the standard deviation? Standard deviation is the square root of this 91/6 that we got minus the mean, which was 3.5 squared. I don't know if, I did put the square on there. That's it. We have that as our guide. And so those formulas are shared with you in the book on page 189. Um, they have this formula for the standard deviation in there, and they always ask for the standard deviation as opposed to the variance. So what's sigma equal to? Well, let's take 91 and divide it by 6 and subtract away 3.5 squared. Hit equals and take the square root of that answer. And so I'm getting 9.20. Okay, so 91 divided by 6, right? Sum of the x squared p of x is minus the 3.5 squared. Okay, I did something wrong before. I was like, that's way too high. So 9 would have been the average distance the points are away. So now I got the square root, and what came for under that 91 divided by 6 minus 3.5 squared came 2.916 repeating. Okay, I'm going to just keep that number in my calculator, hit the square root, pull up that last answer, and I get a more representative one of 1.7. That's the standard deviation. Here, what's the standard deviation going to be? Let's go find out. And so it takes a little bit of work, but from a comparison to chapter 3's work, it's way nicer. So again, 0 squared is 0 times 1/16 is still 0. 1 squared is 1 times 1/4 is still 1/4. 2 squared is 4 times 3/8 is 3/2. 3 squared is 9 times 1/4 is 9/4. 4 squared is 16 times 1/16 is 1. Okay, and so let me make these all 4s. Or just do 1 divided by 4 plus 3 divided by 2 plus 9 divided by 4 plus 1. And we get 5 out of that. Does that make sense? So 1 plus 9 divided by 4 plus 3 divided by 2 plus 1 divided by 4, yeah, is totaling up to be 5. So you don't even need to see what they are individually. So we're almost done. Standard deviation, no problem. Square root of 5 minus the mean squared. This one we don't have to see on a calculator. 5 minus 4, square root of 1. And the standard deviation then is just plain old 1. Okay, and we get it that way. So that's what you're doing in this section. So the other thing that they do is they give you a probability distribution. Here they looked at the number of girls in let me see, casino games. Let's go ahead and look at, well, let's look at the number of girls. And just looking at the questions that they ask. Some of the questions are being asked just to make sure you understand the information that's being given to you. So they should be really easy. Number of girls, which they call X. And obviously this is the probability. So 0 girls has a probability of 0.004. 1 girl has the probability of 0.031. 2 girls has the probability of 0.109. 3 girls has the probability of 0.219. 4 girls has the probability of 0.273. 5 girls has the probability of 0.219. If you're wondering where I'm getting these numbers, I'm copying them down from what's given in the homework problem, right? And so we're not expecting you to be able to come up with these. How they did it is they looked at a very similar type of picture, or they used what's in 5.2, 0.109, 7 girls is back down to 0.031, and 8 girls, and 8 births is 0.004. So that 8 children were being born, and this is the probability distribution. Sorry, it looks a little wonky. So they may ask you for the mean and the standard deviation. No problem. We just have to write down 9 new numbers and add them up, and then another 9 numbers and add them up and do the subtraction. But they also might ask a question like this. Find the probability of in 8 births, find the probability of getting exactly 6 girls. Well, you should be done. If you understand what this chart's giving you, then you know the answer is 0.109. Here is the probability. Here is the probability of exactly 6 girls. Right there. Just right in front of us. That's what that means. And so they want to make sure that you understand what they're meaning when they give you this information. What about B? At least 6 girls. So if you're going to have at least 6 girls, well, that's 6 girls or 7 girls or 8 girls. So what's that going to be? That's going to be 0.109 plus 0.031 plus 0.004. And it's that nice. And they're going to try to get you used to some language that they're going to be using when we step into 5.2. And so notice what we had to do. We had to take each one of those individual probabilities and add them up to 0.144. They're going to ask something like this. Is having 7 girls significantly high? Is 7 girls among 8 children significantly high? And we don't want you to answer that arbitrarily. That is answered by asking the question, is it less than 0.05? So 7 girls. Now when they say 7 girls is high, recognize that when you have 8 girls, you also have 7. That's their mindset. So they're going to combine both of these together. So they're going to use 7 girls and any higher to make that determination. So 7 girls is 0.031. There's only one that's higher, and it has a probability of 0.004. So this is 0.035. Is 0.035 less than 0.05, right? That's when we call something significant. And the answer is yes, it is significantly high. It has a very low probability of happening. How have we defined low? Less than 0.05. So because 0.035 is less than 0.05, the answer is yes. If it wasn't, then we would say no. So for example, D could have said is having 6 girls in 8 births significantly high. And so how would we evaluate that? We would look at 6 and higher, always higher. And you can see even with 6 being 0.109, so I'll write it out, but you should know right away. 0.109 is already above 0.05, but you could add them up like we did in part B and get the 0.144. 0.144 is not less than 0.05, so no, it's not significantly high. It has a 14% chance of happening. That's not high. That's not significant, right? And therefore, we would not call that significantly high. So those are the other style of questions that they're asking. They just want you to get in and look at the information. If they did significantly low, you would do that amount or lower. So when they ask about significantly high, you're considering the probability of being that value or higher. And significantly low is the probability of being that value or lower. And so you're going to add some probabilities together. Something is significant the same way it was in chapter 1 and the same way it was in chapter 4 if the probability of it happening is less than, I think our book puts or equal to 0.05, just to stress where that decimal point is. So again, 6 wasn't significantly high because 0.144 was not less than 0.05. But 7 was significantly high because when I looked at 7 and higher, I got 0.035, which is less than 0.05, so it was significant. Those are the things that you're doing here in 5.1. Email me with questions that you might have, and I can post solutions and any other things that you'd like.